so on. I was going to talk about quantum dots and so on. In the end, I decided to give this particular talk. It's a little bit technical in some ways. I hope it's not too technical, but
are you happy in that photo, Matt?
I think it's Control L. Did you
Control what?
Control L.
So that's what I did. Yeah, so I didn't realise, of course, that Matty would be talking about quite similar things, so it seems kind of appropriate. Yeah, so this talk is going to be about local hidden variables and efficient simulations of certain circuit model computations. In fact, I'll only have time to talk about stabilizer model computations and so on. And this is based on Matt's master's thesis work, the less advertised part of it. So this is the question that we get from funding agencies when we pass being a student and start having to apply for grants and so on. And it's one of those questions that you get faced with. We've now had the power of quantum computing for a long time. By the way, that's, this is the monkeys are going to go in decreasing order of ugliness. So we start here. So this is the sort of question that we're now having to face up to, because it's been the sort of 15, 20 years ago we said we'd have a quantum computer in 15, 20 years. And whenever I get asked this question by, this is meant to be representative of an unnamed funding agency, the answer I want to give to the question is something like this. But unfortunately, I can't give an answer like that. So I have to come up with something that says, well, we theorists, we're working very hard to understand what's necessary as opposed to merely sufficient to achieve quantum computing. And this way we'll be able to make life much easier for our experimental colleagues, and we'll be able to bring this marvelous technology to fruition sooner. And to some extent I actually do believe that there's a lot of work to be done by theorists in trying to work out what the heck it is that really does give us the power of quantum computing, because it might be that there are systems that are much easier that even bad experimentalists, like some of the ones sitting right in front of me, might be able to build it tomorrow, right? If we could actually work out what it was that was required. So these are important questions. Now, what I really, am interested in is keep giving us the money. So the lesson for a theorist is do not ever let experimentalists, as some of the iron trappers are doing these days, tell you, oh, it's just a question of money. If you give us enough money, we can build a full iron trap on a computer. For a start, it's probably crap, and for the second start, they'll take all the money and not give it to us. So don't let them say that. I think that there's still a lot of theory problems out there. Okay, so if I was asked to outline what is the talk about, well, the typical thing that I would say is this talk is about the role of entanglement in quantum computational speedup, which to some extent is what Maddie's talk is about. The relationship between entanglement and non-locality is subtle, so, you might say this is going to be the most boring talk you hear. I didn't know Matty would be here. It's slightly more boring. But really, I'm going to focus on non-locality, which I think is, makes it only probably the second most boring talk you'll hear. So, let's talk about quantum computing and non-locality. So if you have an arbitrary circuit, here's a circuit that definitely has Daniel laser pointer. The laser pointer actually works. So this is a circuit that definitely has non-locality. Why? Because it's basically the CHSH circuit. What I have here are two qubits that are going to start off in a prepared state, and the first two gates here are going to prepare a Bell state. And the output qubits here, A and B, are going to be set to a computational basis input, either 0 or 1. And then these gates here basically just do, so this gate and this gate, do sort of the standard CHSH type measurements. Okay. So I know that this circuit should encode non-locality in some sense. And with a little bit of thought, you realize, okay, what I really want to do is define non-locality as follows. That every system has a hidden variable. That could be anything. It could be the quantum state itself. It could be, some arbitrarily large mathematical object. And every time a system goes through a single qubit gate, well, that can only change the hidden variable for this qubit. But every time they go through a 2-qubit gate, you can change the hidden variables for both systems. And if you think about... yeah, somehow the laser doesn't like to work when I point it this time. So the hidden variable runs along with the qubit. It could be any sort of out-key mathematical object. And when you go through a 2-qubit gate, you're allowed to change the values of the hidden variables for each system. For a single qubit gate, you can only change obviously the variable for that system. Okay. And then you realize that if I think of this as the sort of regular split between Alice and Bob, then this just does a CHSH inequality. So there's going to be no way of sort of reproducing these statistics under this definition of a local circuit. So we're trying to remove the whole issue of space, time, and so on, and just come up with, here's a good definition of locality for a circuit. So if you're happy with that, then I'll set you an exercise. So the exercise is to show that all 2 and 3 qubit circuits have a local hidden variable theory. So I'm going to always be assuming product state input like this. Okay, so well, it's kind of obvious for, say, a 2-qubit circuit because I'm allowing a hidden variable for this could just be the quantum state psi, and the hidden variable here could be the quantum state phi. The 2-qubit unitary happens, and I'm going to always be assuming the final measurements in the circuit are computational basis measurements. So in fact, the hidden variable at this point could just work out what's the reduced density matrix of this possibly entangled state here, and output 0 or 1 according to the statistics of that reduced density matrix. So that would be a kind of trivial example. Here's something slightly less trivial. Here you would say the hidden variable could be initially the state psi and phi. Then when this gate happens, the hidden variable here changes to whatever is the entangled state that you get when you apply this unitary on these two things. And that hidden variable comes along here. This hidden variable, since it's going to be measured anyway, could just spit out a 0 or a 1 basis with the correct marginal probabilities. But this one here runs along, and now it knows what this entangled state is here, and then it knows what happens when you apply this unitary U2 to sort of chi in that entangled state, and then it can spit out the marginals. And with a little bit of thought, if your name is Matt Pucci, you can kind of work out how to show that every 3-qubit circuit has a local hidden variable model. It doesn't matter how I sort of cascade 2-qubit gates like this. So in the previous slide, we actually had a 4-qubit circuit, so we know you can sort of get, we had a 6-qubit circuit, so we know that you can get, we had the 4-qubit circuit. We know you can get nonlocality for that, but you can't get it for a 3-qubit circuit.
Sorry, so this result is important how you split when you want to get the, is it like depending on how I split my Alice and Bob, I always get the
You see, I'm trying to define non-locality without Alice and Bob. So it's really each system has a local hidden variable that runs along with it. And that it only is when it interacts, i.e. when it goes through a unitary with another system, their local hidden variables can change. They could become some completely different mathematical object if you wanted. But then at all other times you can think of them as they're not allowed to communicate. Probably draw some kind of crazy space-time diagram. Okay. So now, the question I'm going to ask is, so we know 4-qubit circuits don't have a local hidden variable theory. So let's ask whether stabilizer circuits, things that are built from only gates, stabilizer gates, things that are sort of normalized of the Pauli group, do they have a local hidden variable model? And the first thought of anyone you ask is, well, no, because similar to the sorts of things Maggie was talking about, you have a GHZ paradox, even if you just have stabilizer gates and circuits. But if you go and you look at trying to write down the GHZ paradox as a circuit, here's the sort of thing that you would end up writing down. You would say, well, I can create the GHZ state here by sort of these gates acting on fixed computational basis input states. And the qubits that are going to choose, remember in the GHZ paradox, I've got to choose x and y, between x and y basis measurements. Those will be set by either a 0 or 1 input here. And these are the gates that actually do a kind of a choice of an x basis measurement or a y basis measurement, because I'm forcing that these final measurements are computational basis. But this isn't a Clifford circuit. A controlled S gate is not a Clifford gate. Okay. So it's clear that, okay, if you just think in the computational, in the circuit model, where you're not sort of allowing these kind of, say, the same sort of choices as maybe you would in the measurement-based model, this doesn't give you non-locality from, for just pure stabilizer gains. Although, if I allow you to choose an input that's not a computational basis input, so you're forced to still have a stabilizer input, a stabilizer state, so one of the eigenstates have the x, y, or z, then you could reproduce GHZ non-locality, because this simple circuit, for example, by choosing whether to input the plus or minus here, or the eigenstates of sigma y plus I or minus I, you can choose whether or not you get an effective x or y basis measurement on this qubit. So you could build that into a GHZ circuit, and you would get GHZ non-locality, and all your inputs would be stabilizer states, and all your gates would be stabilizer gates. So I failed to even come up with a local hidden variable model for stabilizer circuits with inputs that are stabilizer states. So even arbitrary stabilizer input circuits are non-local. But so what I'm going to do is I'm going to restrict even further. I'm going to say, let me take stabilizer circuits with arbitrary computational basis input. Okay, so you can't sort of choose, like I'm doing in this circuit, between, say, plus I or minus I and so on, that you really got to fix a computational basis input. So really pure circuit quantum computing. Okay. So now, at least for a naive local hidden variable model, even that's impossible. Here is a naive, here's a circuit that I'm going to use by load and rest of the tool. And if you work out what this circuit does on just sort of a 0, 0 input, it takes you to the state psi plus, which means that if you do a computational basis measurement here, you get anti-correlated outcomes. Now, if you take a naive local hidden variable model, I'm going to define it as follows. For each qubit here, you use two classical bits that are labeled little x and little z. Okay. So there's 2 bits per qubit, and these bits are basically just going to encode the value of the x and z sort of Pauli eigenstate. So x is 1, that x being 1 or 0 corresponds to kind of like getting the plus or the minus state if you did a measurement of sigma x. The z being 1 or 0 corresponds to getting sort of 1 and 0 for a z basis measurement. So it's just a sort of a 2 classical bit gain. And in this naive local hidden variable model, when the 2 bits encounter a gate like the Hadamard gate, the Hadamard gate will act in the way that that gate acts on the Pauli x and z eigenstates. So the Hadamard gate takes Pauli x to Pauli z and Pauli z to Pauli x. So here it's just going to swap the value of the 2 bits. That's how a Hadamard gate will act. The C0 gate will acting on the sort of bits that encode the z, Pauli z. Well, that's just a standard computational basis C0, that the target bit of this qubit. So now you've got to imagine there's a C0 gate acting between 2 qubits here. This just goes to z plus z prime. But in the plus minus basis, the C0 kind of acts backwards. It uses this second qubit as the control and the first qubit as a target. That's how C0 gates act in the x basis. So this is just a naive local hidden variable model. And, in the spirit of continually telling you things that are useless and don't work, this also doesn't work for implementing this circuit. So here is how you would go along. You would say, okay, in this circuit, the first qubit x could just be random because I've fixed the Pauli, I fixed the input to be 0 for the z bit here. So this would just be a random bit. The Hadamard gate sort of swaps the 2 bits. So here nothing happens. Then I do the C0, so that sort of adds this to 0, leaves this the same. Copies this up here. I go through a Hadamard, which swaps these 2. I do the C0 again. I do the Hadamard. And when you look at the output bits here, which are the bits that are going to give, because I'm going to do computational basis measurement here, are going to tell me what the computational basis output will be. you see that they're correlated in Z. I've got the same bit here, even though it's sort of built out of these two random bits, I'm going to get the same outcome. So I failed to reproduce what quantum theory says, which was that I'm going to get anti-correlated measurements in the computational basis. So I'm still, obviously not very successful. But I'm going to keep going with this thing which isn't working, just to torture you some more. So I'm going to draw it out as a classical circuit. So here's a classical circuit for that local hidden variable model. It's like the x bit here can just be thought of as input as random, the z bit is input as 0, the Hadamard does a swap between the two bits. The C naughts sort of act forwards and backwards, as I said, and so on. So this gate is kind of a swap here. Okay. So I've drawn out this thing, and we've just seen by explicit calculation that this doesn't work. It gives correlated computational basis outputs. But then here's a kind of curious observation, that if you add a classical naught or a classical x, you could think of it as, on this particular bit, for example, then the circuit does reproduce the quantum predictions. And it does so even if you don't restrict yourself to the inputs 0, 0 on the circuit, but if you allow any computational basis input. So it could just be a coincidence, right? I've found a particular gate here that suddenly makes the circuit reproduce arbitrary computational basis sort of inputs and measurements. But what I'm going to, what the sort of the rub of this talk, the essence of this talk is the following theorem. That in fact any stabilizer circuit with computational basis inputs and measurements can be simulated by a local hidden variable model. And basically the whole game is to find a way of taking a circuit like this for this naive local hidden variable model and then finding appropriate gates to put on that circuit, and then you will reproduce the quantum predictions. Even though you've got all in the quantum circuits, you have all these entangled states and gates and so on. Okay. Now it's a messy thing to prove, a really messy thing to read if you have to read maths thesis. I'm going to try and give you the essence of it. So how we do it is, well, we're going to break the stabilizer circuit into Hadamard gates, S gates, and C naught gates. You can always do that, and doing that's not going to change the sort of locality properties of the circuit. Just like the example I gave you, we're always going to use 2 bits per qubit, 2 classical bits per qubit. And we're going to follow the same sort of rules that the gates here act like the stabilizers act like the Paulis get conjugated by the equivalent unitary. So the Hadamard swaps the x and z, the C naught acts like this, and you can easily work out that the S gate sort of acts like a C naught backwards from the Z bit to the X bit. So if we were talking about so what I'm going to do now is do something which is a bit odd, and this takes a little bit of getting used to. I'm going to write down stabilizers for the local hidden variable model. So these are not stabilizers, not the quantum stabilizers, these are stabilizers for the local hidden variable model. So they're all built out of Z's, because the local hidden variable model is just classical bits. And if you were asked for this sort of 2-bit model, how does this gate act? So what you would do is say, well, if I fix the inputs here to be computational basis inputs, then the input 0, 0 is basically given by the pair of stabilizers Z identity and identity Z. And if you act a swap, well, you just swap Zi to Iz, Iz to Zi. Okay. Whereas here, if you look at, let's say, our input 0, 0, 0, 0, then the C naughts, we know how C naught gates act on Z. So Z I evolves to Z I, because what's the easiest way to see that? So this flips. When I act backwards, I flip. So when you run a Z through the target of a C naught, it kind of clones itself. That's the best way to think of it. Z, Z. So this is for computational, but this is for all zeros input. If you wanted to fix one of these bits to a 1, well then you would just put a minus sign, because 1 is the eigenstate of sort of minus C. So you would have a minus sign here, but the minus sign would just propagate through the circuit and be a minus over here. Okay. So this just looks like a kind of a messy mathematical game. But now what I'm going to do is I'm going to define some operators that are actually the tensor product of two Pauli operators. So x tilde is going to be defined as z tensor identity, y tilde is going to be defined as z tensor z, z tilde is going to be identity tensor z. And these operators obey this relationship, x tilde y tilde equals z tilde. But they commute, so it's also equal to y tilde x tilde. So this is sort of a kind of a dumb Pauli algebra. Okay? Everything here was built out of z's. It looks like just a dumb kind of version of Pauli algebra. So why do I call these blind stabilizers? Anyone other than Matt who failed to work it out? Why are they blind stabilizers? What's different about this relationship with the Pauli relationship?
No phase.
No
So
eyes.
minus one. There's no eyes. Oh.
Right, none of you are allowed to be my PhD student. Alright, so if you take these blind stabilizers, then you notice the following, that this relationship here takes x tilde to z tilde and z tilde to x tilde. That's what the action of this gate does. And that's actually what a Hadamard gate does. A Hadamard gate conjugates x to z and z to x. Similarly, if I go through these the blind stabilizers for how does a single qubit, two qubit C naught gate acting on x identity, z identity, ix and iz would give out the same relationships but just without the tildes. So we see that the blind stabilizers mimic real stabilizers, but just up to phase in some way. So for this circuit back here, the quantum, if you evolved, you said I want to look at the 0, 0 input and evolve, the input stabilizers here, conjugated through the circuit, you would get y tensor y. This would be sort of regular Pauli. These would be the generators of the output for that, just as regular Pauli matrices. Here for the blind stabilizers, well, z tilde I tilde goes to y tilde, and so you just sort of put tildes on everything. The problem is that the states are somehow not the same, because if you go and you look at the full subgroup of the Pauli group that's generated by these guys, here you would get a minus zz, whereas here you're going to get a plus zz. Because the blind stabilizers don't sort of pick up the same phases that the Pauli group does. And not only that, but it's these guys that are going to be important for us, because I'm going to call products of z's, so elements of the Pauli group that just consist of z's and identities, the computational subgroup, and so they're just sort of products of z's like this. And they are the things that determine what the statistics are for measurement in the computational basis. I'm only interested in final measurements in the computational basis. To see that, well, you just say, if I wanted the probability of obtaining a 0 on one qubit and a 1 on the other, I could take, here would be the projector onto 0, here would be the projector onto 1 for the second qubit. Expand it all out, you just get expectation values of things that are products of z's. So the upshot is that, if I can kind of make the computational subgroups agree between blind stabilizers and real stabilizers, then I'll get the same statistics for measurements in the computational basis as quantum theory does. So the game is I have to find ways of kind of correcting that. Here I went through and I just put tildes on, everything goes through the same. So for example, z1 tilde, z2 tilde, remember z1 is iz, that makes sense because the second bit here always corresponded to Pauli z, as it were. So, computational basis measurement just corresponds to sort of looking at the second classical bit associated with each qubit. Alright, so the problem is trying to get this minus sign on this guy here. Okay, I failed to get it on the generators of whatever this output state is, but I kind of want to get it over here. I want to do that. Well, if I put a minus over here, So that flips, that's like saying take this input to be 1 instead of being 0. Then that minus sign just carries through because it's just a phase, you can conjugate it through all the gates however you want. And of course you get a minus sign over here that the quantum thing doesn't have, but you get the right minus sign on this ZZ, you get Z tilde Z tilde. And that's, that's going to mean the computational subgroup here is identical for both things. So then measurements in the computational basis will be identical. Same statistics. Alright, so the upshot of the whole game is the following, that it's trivial to go through and conjugate the blind stabilizers the same way as quantum stabilizers go through. But at the end of the day, if you had n qubits here, this would be some exponentially large set, the subgroup of the output of the state. So you would have to run through and find all the computational basis elements of this group, and then find ways of flipping these generators here, and then taking that back and flipping these signs here, so that the whole thing works out. And to see that that's doable is actually non-trivial, and it's going to take me sort of 2 slides where I presume most people will zone out a little bit. But the thing I should say is that not only is it doable, we recently found that we can do it efficiently, so we can actually find a polytime algorithm for doing it. So we've got to sort of find which guys, where are the knots, where are the minus signs we're going to put. Okay, so this is just an overview of the strategy. This is a generalization of what I said. We look at sort of take the input stabilizers, pull in Z1 through Zn, conjugate them through the circuit, you get an output set of stabilizers for the output state. Okay. Then what we're going to do is we're going to take these guys and try and work out a set of generators. So these are the generators for the whole output state. I want to find a set of generators that include a set of generators for the computational subgroup. Okay, so this is a new set of generators for the output, that actually these guys will be just products of Z's and identities. So now I've got a new set of generators for the computational subgroup. Then I've got to find any of these that are negative, and I've got to work out, sort of going backwards, this mapping. I mean, these are the same group, but I've got to kind of go backwards, find out which generators I need to multiply by minus I here, then take that minus I back to the input, and I'll have sort of corrected for these incorrect minus signs. And then I can just write down the local hidden variables. Alright. And the point I should make is that it works because for the computational subgroup, the quantum and the blind stabilizers agree, even on the phases and so on. So getting the generators right kind of gets everything all right, because they're sort of all constructed out of Z's. Alright. So the procedures, so step 2 is you've got to work out a new set of generators built that have generators for the computational subgroup. A way of doing that is to do a kind of a Gaussian elimination. People have used Gaussian elimination for stabilizers. Here we're going to use a slightly different type where we do the elimination in such a way that we don't care once a column has Z's and identities in it. We're fine with it. So if this was your set of output stabilizers and here you had some Z's and X's and Y's, you sort of take the first guy that's not a Z, you fix him at the top left, and then you multiply any other guy, any other rows, because this is just group action, keeps them sort of independent generators, just multiply them by either one of these guys with an X or one of these guys with a Z, to kind of force them to be either Z's or identities. So you can multiply this X by this to get an identity, for example, or this Y by this to get an X, this Y by this to get a Z, and so on. And then you'll have fixed the first column to consist of either an X or a Y, and then a bunch of Z's. And then you can go along to the second column. Sometimes you have to reorder things a bit, and then do the same, fix this guy to be not to be an X or a Y, and then some Z's and identities. And you sort of build up a triangular form like this. And then when you get to something like this, you see that once you've sort of run out of X's, Y's, you'll be left with stabilizers that are all built out of Z's and identities. and these are the generators of the computational subgroup. Okay. So this is an efficient algorithm, it turns out, to find generators of the computational subgroup. It's slightly more messy than the way I described it. But yeah, so once you've done that, you can look at those guys, and now the sort of real tricky part that we needed the help of a postdoc of mine, Gary McConnell, who sort of grew up doing number theory, is the following, and this is the most technical slide, and I probably will not dwell on it too much. But basically, we want to work out how do we flip. So we want to flip any of those elements of the computational subgroup that are negative. We want to multiply them by minus identity. So we essentially get a different set of generators. We go through any that are negative, we multiply by minus identity, so I can get a different set of generators. And what we want to do is show that there's a different set of generators of the G's. So remember, these are kind of equivalent in some sense. We want to get a different set of generators of the G's, so we want to flip some of these with some phases that are called EI, such that we generate the same group H prime, and then once we've worked out what these E's are, we go back and flip them as flipping the generators at the input. So it's a messy procedure. Maybe I'll just skip through it very quickly. The Gaussian elimination gives us kind of a mathematical relationship between these H's and the G's. We essentially can invert this relationship and use whatever is the matrix that gives us kind of the relationships between the G's and the H's to act on these kind of phases, the big E's and little E's, and it's a few steps of algebra that I'm now going to skip because it sort of looks like doing general relativity and quantum mechanics, but it does work out. Okay, so all of that is just the math. That doesn't really explain where the heck did this construction come from. Okay, these sort of constructions, you can't suck them straight out of thin air. So now to give you some intuition for where it comes from. If you look at these line stabilizers, x tilde is z tensor identity. If you ask, what is the quantum state that corresponds to x tilde? Well, it's projected onto 0 tensor identity over 2. This one is a mixed state projected onto 1 tensor identity over 2, and so on. So you can look at the mixed states that correspond to the blind stabilizers. Because there's 2 Paulis for the blind stabilizers, there have to be mixed states because you've only got sort of one generator, like Z, and so on. And now if you sort of expand these out in the computational basis and look at, you've got 0, 0, 0, 1, 1, 0, and 1, 1, these are the 2 classical bits, and look at these probability distributions over these 4 classical bits, they just become probability distributions half, half, 0, 0, 0, 0, half, half, and so on. And then those of you who've worked in foundations for a while would recognize these as Rob Speckens' toy bits from his toy theory. So basically the toy bits of Rob's toy theory are the eigenstates of these blind stabilizers as mixed states. And the first time, many years ago, that I suggested to Rob this mapping, in fact, without the intuition about the blind stabilizers, but just because we were talking about efficiency of computation, this was the reaction I got. He didn't want to have any relationships between quantum bits, states, and toy bits. But this is certainly, I think, now clear to me that this is the right way to think about this. Alright, so really what we've done is found a way of kind of taking the toy theory and taking a circuit where we have gates acting between the toy bits, and we have to compute some kind of corrective NOT gates to do with the input, but we've basically shown that Speckens' toy theory gives a local hidden variable model for stabilizer circuits that have computational basis input and output. Okay. So Roll would say this talk is about contextuality in quantum computational speed up, because the toy theory is a non-contextual theory. So maybe it's only the third most boring talk you hear, and you notice that I realized after my pages of sort of messy algebra, this is what you look like at this stage in the talk. Alright, so let me just have an aside also just to maybe set the stage for what John will talk about later. It's easy to find a stabilizer circuit. So this shows the toy theory works for computational basis input and output. The toy theory can't cope if you're allowed arbitrary product stabilizer input. And here's a simple sort of thing that shows it. So in the toy theory, these are the four ontic states, which are labeled with two classical bits. And this state is what we would call Pauli psi epistemic. This ontic state can be prepared for each of three different eigenstates of Pauli x, y, and z. It's slightly different mapping to what Rob uses. So when you look at the real state of one of Rob's toy bits, it could be compatible with preparation of any one of three different quantum states. Okay. And so then it's easy to find a circuit which the toy theory cannot deal with. Here's a simple one that just consists of do a C0 gate and measure the one toy bit in the X basis and the other in the Z basis. Okay. So the way, so imagine that the measurement devices see that the ontic state for the first toy bit is 0, 0, and for the second toy bit is 0, 0. Then it looks at this thing here and it goes, the input could be any of these combinations of plus zeros and nines. And the problem is that it's not sure kind of what the quantum state input is. And if the input was plus and plus, then the X outcome would have to give plus 1, because if I take plus and plus, evolve it through a C0, I get plus and plus. So the X outcome is the measurement on the first qubit here, so it would have to be plus 1. The outcome, if I had an input 0 and 0, the Z outcome here would have to be plus 1, because 0, 0 evolves through a C0 to 0, 0. But if I happen to have input here plus I and plus I, X and Z would need to be anti-correlated. And that's in contradiction with both of these being plus 1. So this is a simple circuit that fails, but the reason it fails is that in the hidden variable theory there is kind of multiple quantum states associated with just one value of the real state, the local hidden variable state. And you can use this to rule out kind of similar Pauli psi epistemic models. But here the issue is that associated with one thing to note is that associated with one value of the hidden variable there's three different quantum states. So what if we're interested in situations where associated with one value of the hidden variable there's only two different quantum states? So that's an aside on the aside, that's what John will talk about. This is this paper that says the quantum state cannot be interpreted as a diagonaloid or category or whatever it is. John would love. And in that paper the measurement basis is a basis of Clifford states, which is interesting. But you can't measure it as just a circuit and then computational basis. It actually requires an adaptive strategy. You could measure first the YY observable and then based on that outcome do one or two different observables. So it's sort of an interesting measurement. And now this is something that I have a vague intuition about that I think Dan and Matthew will understand better, which is that measuring stabilizer bases, there's sort of decreasing levels of power. Like just a pure stabilizer circuit is somehow less than stabilizer circuits plus feed forward, which is less than basis. So this is a basis of stabilizer states, but you just can't measure using kind of stabilizer operations at all. So these are sort of different. These are different levels of strengths of stabilizer bases. I don't have a good intuition for what's the difference in these different things, but I think hopefully it'll start getting clear soon. Alright, so conclusions, open problems. For computational basis input and output, there is a local hidden variable model for all stabilizer circuits. It's based on Rob's toy theory. It's still an open question if the same is true for match gates. So you can ask, match gates are another efficiently simulatable set of circuits, and we have various, let's say math has various sort of partial results in numerics that make us think that maybe it's still true to some extent for match games. It's an open question that I think would be very interesting in the context of things that, like Matty and Dan and so on, whether this local hidden variable model can be constructed by a parity our classical computer as opposed to what we've required is, the computation is efficient, it's in P, but it's not in parity L. And there's these connections that Dan and Jan and various people have found between the power of parity L classical computers of measurement-based quantum computing being universal, whereas with circuits they're not. And so there's a lot of things I think are still sort of floating around that need to be clarified. And of course the last question is whether you're going to hear, well, this you answered already because you heard Matty's talk, so I'll leave it at that. Thanks.
So, any questions?
It's really for a real computer science audience, not a fake computer science audience.
Ben?
So this, I don't know whether this is a question or sort of an observation. So in your model, you have to know the quantum circuit in advance before you can construct the model for it. You can't sort of do it on the fly. And that would seem to be impossible because of the controlled, you need controlled cliffs to sort of turn on and off your circuit. But does that, but then there seems to be sort of two different roles here in your simulation. On the one hand, you've got your circuit, which you have to specify in advance. And then you have your inputs, which you're allowed to choose freely. Is that right? And is there some sort of duality between those two things? Can you, if you fix the inputs, can you then change the circuit? I mean, maybe if you fix the inputs, the whole thing becomes trivial. I don't know.
Yeah. No, I mean, so it would be certainly nicer to have something where you went on the fly, but
I think you can't have that because then you don't control the difference.
so, yeah. But you can imagine something's a little bit weaker than the way that we've done it, where you know the whole circuit, for example, go through. So we're still playing with that. But yeah, I don't know. I don't know what that trade-off is. I mean, that might be a intuition, as you say, the choice of versus.
Is why it leads to coming up with a new class of classical simulating quantum stuff? You're trying to target match gate and stabilizer states thing, but there's lots of other family of classically simulatable quantum computation that none of this approach of compact representation or entanglement-based arguments might have been considered. Could it be that there is some general classification that you give your quantum circuit, if I could construct it, of course if I can construct it, then it's classic simulatable, but it's just bringing, it's more or less like the other direction of the question that we come up with the new classes that we haven't realized before, just doing backward of your procedure.
I mean, so you know, what Dan's question targeted was something which is relevant to that. Like, if what you're interested in is how do I simulate quantum computers, you don't care if there's a polynomial algorithm that you then have to invert to get out this circuit. So if you think that this is how reality is and how nature's evolving, well then it seems weird because it's kind of backwards causation. So yeah, you know, it would be great to have other families which, even though it's a bit of a weird type of construction of a local hidden variable, kind of look circular, like, oh, you know, it's not match gauge, it's a stabilizer, but I can find some sort of thing. That would be great. I should say, as a polemic, that this construction should have been discovered by Bob and his students, because these guys wrote down kind of the formal mathematical structure of the Toy theory, what the relationship is with the stabilizers, and so on. And so, I think, but more generally, I think that if the category theory side want people like me to actually learn how to use the category theory, they should look for concrete things like this that I go, oh, well, I need to go and learn the category theory so I can understand how to construct these things. And yet, that's not the sort of thing that I do. That's my academic challenge.